Hello, everyone. Thank you for joining us today for the presentation of our paper titled CausalPC, Improving the Robustness of Point Cloud Classification by Causal Effect Identification, which has been accepted by CVPR 2024. This research was conducted by the Wizard AI Group at School of Computer Science of Fudan University. Our presentation begins with an overview of CausalPC. CausalPC is the first to analyze point cloud classification from a causal perspective. We leverage graphical causal model and front door adjustment to model the task of point cloud classification. The proposed method substantially improves the robustness of existing classifiers regardless of architecture. Let's start with the key problem we are addressing. Point cloud classification is an essential task in many applications, such as autonomous driving. It categorizes a point cloud X to label Y. However, recent studies have shown that deep neural network models for PC classification are vulnerable to adversarial attacks. Attackers can slightly perturb the point cloud in ways that are imperceptible to humans, but can drastically mislead the model's predictions. Existing defenses, such as adversarial training or input-oriented approaches, often fail to generalize well against diverse attack strategies. Motivated by this, we propose to analyze point cloud classification from a causal perspective, inspired by how humans recognize 3D objects. Our key insight is that, regardless of the specific attack strategy, the resulting adversarial examples still bear a strong resemblance to benign point clouds from the human perspective. This suggests that we should focus on identifying the causal effect between the point cloud data and the classification, rather than relying on statistical correlations. To achieve this, we first construct a causal graph to model the key variables involved in point cloud classification: the physical object, the structural information extracted from the point cloud, and the hidden confounders that may influence both the input and the prediction. We point out that existing classifiers fail to model the hidden confounder U, which leads to their poor robustness against adversarial attacks. To complete the causal effect identification for PC classification, we then leverage the graphical causal model, GCM, framework, and the front door adjustment technique to formally define and estimate the causal effect. For the ease of actual implementation, we apply Monte Carlo sampling to approximate the causal effect identification formula. Technically, CausalPC comprises 3 submodules to realize this causal inference process. The structure extraction module uses farthest point sampling to capture the key structural information of the point cloud. The point cloud reconstruction module employs an upsampling network to recover the details of the original object from the observed point cloud. Finally, the joint attention classification module fuses the structural and reconstructed information to make robust predictions by explicitly modeling the causal relationship between the point cloud and the classification label. Our extensive experiments on benchmark datasets demonstrate the effectiveness of CausalPC. Compared to state-of-the-art defense methods, CausalPC can significantly improve the adversarial robustness of various point cloud classifiers. For instance, the classification accuracy of DGCNN on the ModelNet 40 dataset increases from 29.2% to 72.0% under adversarial attacks, outperforming the best baseline by 30 percentage points. In ablation study, we also show that causal modeling modules collaborate with each other to improve the overall model robustness. In the right side plot, we further show how the Monte Carlo sampling works in our causal modeling implementation. It can be seen that causal modeling dramatically reduces the impact of adversarial perturbation. In summary, CausalPC is the first work to tackle the point cloud classification problem from a causal perspective. By identifying the causal effect between the point cloud and the label, our framework achieves remarkable improvements in adversarial robustness, paving the way for more reliable point cloud-based applications. Thank you all for watching this video. If you have any questions, please contact us through our email or visit the website of our group to check out for more incredible AI security works.